Hey guys, welcome to the last Flip Classroom video. Some of you might be excited, but others hopefully are disappointed by this, but here's the last video. Today we're talking about similar polygons, and that's a fancy way of saying shapes. So we've taken a look at what makes two triangles similar. Remember, the corresponding angles must be equal or the corresponding sides must be proportional. So you have to check either that all the angles were the same in both triangles or compare corresponding sides in a fraction to see if you get the same scale factor for all of them. So today we're going to see what makes other shapes similar, other than triangles. So for other shapes, the idea is quite similar to triangles. Notice I'm using this word here again. Two shapes other than triangles are similar when their corresponding angles are equal and their corresponding sides are proportional. So with triangles, you could check one or the other. For other shapes, you have to check both. All right, so make sure that both of those things are true. That's because of situations like these. So for example, if we had two rectangles like this, clearly they each have the same angle in their corner. They have the same angles, 90 degrees in each corner, but the sides clearly aren't proportional, meaning they're not similar shapes, right? This one is stretched out in one direction but squished in the other, so this is not proportional to this one. They're not similar shapes, even though their angles are all the same. Or like this situation here. In this case, this shape here, it is enlarged by 2, right? The length is twice as long, the height is twice as big, but clearly the angles are not the same, so they're not similar shapes. So even though the sides are proportional, the angles aren't the same, so they're not similar shapes. So both angles and proportional sides have to be true for other shapes. So for example, here are two similar pentagons. We're being told they're similar, and it's true because look at their angles. They're all the same, 95, 80, 80, 120, 105, 140 for both shapes here. And then look at the side lengths from here, from this one to this one. Multiply by 2, get 7. Multiply by 2, get 4. Times 2 is 6. Times 2 is 4. And times 2 is 3. So each side here is twice as long, and each angle is the exact same. So these are similar shapes. In terms of names, this one here we'd call pentagon A, B, C, D, E. This one here, all the letters have a little tick mark after them. That's described right here. Those tick marks beside the letters are read as prime. All right, so we'd say A prime, B prime, C prime, D prime, and E prime. What that's telling us is that they're indicating corresponding angles on the enlarged figure compared to the reduced figure. So basically, A prime corresponds to A. This one corresponds to here. B prime corresponds to B, and so on. All right, so that's just a kind of another way of naming a rectangle or another shape, just by putting a tick mark after all the same letters from the original one. Like we saw, all corresponding angles are equal, all corresponding sides are proportional, so these are two similar shapes. So we could say either pentagon A prime, B prime, C prime, D prime, E prime is an enlargement of the other pentagon with a scale factor of 2, meaning this one's twice as big. Or we could say pentagon A, B, C, D, E, the smaller one, is a reduction of the pentagon, the other pentagon, with a scale factor of half or 0.5, right? Because this one's half the size. So since they didn't tell us which was the original shape and which was the diagram, it doesn't matter which way you think of it. If you think about it as twice as big as the other one, that's great. If you think about it as half the size, that's great too. Like I said last time, I like thinking of or having the bigger number being the diagram, meaning that this one would be twice as big. That's how I think of it. Let's look at some examples. So the question says, identify which rectangles are similar shapes. So we have 3 of them here, but they're not all similar to each other because the sides might not be proportional to each other. So they each have 4 90-degree angles in their corners. So we just need to check the lengths and widths for whether they're proportional or not. Okay, so I need to compare each rectangle to every other one. Okay, so I will compare these two in red. I'll compare these two in green. And I'll compare these two in blue. All right, so let's do the red one first. Like I said, I always like having the bigger number on top of the fraction. So compare the length here to the length here and see what we get. Okay, so we have 8.5 as the length on top and 5.25 as the length on the bottom. So here you calculate what that would give you. You go 8.5 divided by 5.25, and you get this number. So we'd say let's round it to 6.2. And then compare the widths. Okay, so we have 2.5 here and 1.5 here. So bigger one on top, 2.5 over 1.5. What do we get? 2.5 1.5 over 1.5, we get 1.66 repeating. So they are close, but they're not identical. So these two are not similar triangles. Okay, now let's compare the green one here. So this one to this one. All right, so again, this one's slightly bigger, so I'll put these numbers on top of the fraction, the length and the width compared to the other one. So I want to go, whoops, I thought I was going to do green here. So I go 8.5 on top, 8.4 on the bottom, and then I go 2.5 on top and 2.4 on the bottom. So I want to do these two divisions to see if I get the same thing. Okay, so I go 8.5 divided by 8.4 equals, I get 1.012. And then let's do this one right here. So I go 2.5 divided by 2.4, and I get 1.042. So again, these are close, but no, they are not similar triangles, or similar rectangles, sorry. Now this last one, let's check this here. So I'm going from this rectangle to this one. Again, bigger number on top, and for both the length and the width. So I want to go, and again, I thought I switched colors. So I want to go 8.4 over 5.25, and then 2.4 over 1.5. So let's do those two divisions and see what we get. 8.4 divided by 5.25 gives me 1.6. And for this one here, 2.4 divided by 1.5 gives me 1.6 as well. Those are the same, so yes, these two rectangles are the same, so I'll name them. I would have E, F, G, H, and J, K, M, N are similar. All right, so that's by comparing length and width. We find out that these two are similar, but this one's not similar to either of the other two. Let's take a look at one more example. So these two octagonal garden plots are similar. So that we're told that yes, all the angles are the same, all the sides are proportional. We're told they're similar. And so we want to do a couple things here. So list 3 pairs of corresponding sides and 3 pairs of corresponding angles. So when it comes to sides, since they're facing the same way, again, it's easy. I'll start up here. This one is AB, and it corresponds to this one up here, which is IJ. How about another one? Again, there's 8 corresponding sides, 8 corresponding angles. Doesn't matter which ones I pick. Let's go with this one here. CD corresponds to this one here, KL. And one more, let's go with the top one, EF corresponds to this one here, MN. Okay, and how about angles? Well, let's start down here. Angle G and angle P are corresponding. So angle G and angle P. This one here, H and Q, same thing. Angle H, angle Q. And one more, let's go to the top, N and F. So angle F and angle N are corresponding. So again, it's pretty easy to identify, but it's just a good skill to have to be able to pick out, okay, this one and this one are kind of in the same spot. So we want to calculate the length of GH. So that's this one here on the bottom. I need to figure out how long that side is. So what I need to do is look at these and see if there's any corresponding sides where I know the length of both of them. I know this one here, but I don't know this one here. But look up here. I know 5.4 up here and 8.1 up here. So again, I can compare these. Okay, so I want to set them up as a fraction. And like I said, that doesn't tell us which is the original. So I'm going to take the bigger number on top of my fraction. Okay, so 8.1 over 5.4. So 8.1 over 5.4 gives me 8.1 over 5.4, whoops, 5.4 equals 1.5. Okay, so this is telling me that the garden plot on the right, this one here, is 1.5 times the size of this one. And I need to figure out the size of the bottom here. It's going to be smaller and I have a number bigger than 1. So to make this number smaller, you have to say, well, do I multiply or divide by 1.5? Try both. I know to make it smaller, I need to divide by this number. So I'm going to do that. So 32.4 divided by 1.5 should give me the length of GH down here. So let's check. 32.4 divided by 1.5 gives me 21.6. All right, so does that make sense? Yeah, this one's smaller than 32, and the number I get is smaller than 32, so that would make sense. That would be 21.6 meters. One last question here. Calculate the length of NP. Okay, so NP is this stretch here, from N to P. Okay, and that compares to 27. We know that the scale factor is the same, 1.5, so this is going to be 1.5 times bigger than 27. So since it's that many times bigger, I can say, okay, well, I have 27. I know it's going to be 1.5 times bigger. And what do I get? 27 times 1.5 equals 40.5. So again, let's just check to make sure that makes sense. 40.5 up the side. This side is longer than this side, so yeah, that makes sense. And it looks like the longest side and the biggest number, so that makes sense to me. All right, so that's how we can use what we know about similar shapes to solve problems like this. Again, comparing two corresponding sides, getting a scale factor, and using that for the rest of the sides. All right, so that's all for similar shapes. If you have any questions, if you're watching this at home, write them down. If you're watching in class, feel free to call me over and ask me what's going on. Yeah, hope you enjoy the flipped classroom. Thanks.